Hi everyone, my name is Abdullah Mubarak, and in this video, I will walk you through my attempt to reproduce Autothrottle, a B-level microservice resource controller published at NSDI 2024, and also my analysis of where it can be extended. Before we dive in, let me introduce myself. I am a fourth-year undergraduate student at Bandung Institute of Technology, the #1 engineering university in Indonesia. My research interest lies at the intersection of machine learning systems and resource control. Recently, I also have growing interest in serving systems in general, like microservices. My research experience mainly comes through SHAIR, a research group guided by Professor Hadi Gunawi from the University of Chicago. Through this program, I read over 15 papers in depth and skimmed 35 plus papers from top conferences like OSDI, SOSP, NSDI, and MLCs. I also reproduced two papers on Chameleon Cloud. The first is Flex LLM, where I reproduced the full experiments, and the second one is Autothrottle, which I will explain further. In total, I spent over 50 hours understanding the paper and the code base. For the setup, I used three Chameleon Cloud Compute Skylake nodes, each with 24 cores, so 72 cores in total, compared to the original paper which used 5 nodes with 160 cores. I only reproduced the social network experiment, and I used a newer Kubernetes version, which is 1.28 compared to the paper's 1.20, and that's why I needed to update funnel to a compatible version. The original K8s package source from the paper was also deprecated, so I had to migrate to the new one. Other than that, my contributions are modifying evaluation.py and setupnode.sh to accommodate the hardware differences. And I also created notebooks to generate 3 figures and 1 table from the paper using the experiment results. The most important lesson I learned is that I did not calibrate 3 critical variables: threshold multiplier, constant RPS, and the initial limit to match my lower hardware specification. This caused the SLO attainment to be basically zero throughout the experiments, and the effect cascades through everything. First, at Tigusik, looking at the results, the paper shows P91 latency staying under the 200 millisecond SLO. And the SP allocation tracks the pattern of the latency quite cleanly. And the two lower graph, we can see that the two throttle targets are relatively stable and reflects the two surface groups classification. So the left one, the group 1, which is high resource usage, has a consistently high targets, while the group 2 has consistently lower targets. Looking at my results, the P91 latency went through the roof, almost 40 times the SLO, and CPU allocation and usage didn't follow any coherent pattern. And I think the most notably, the throttle targets are more erratic with no distinct difference between the two groups. And the root cause is that with zero SLO satisfying samples during the warm-up, the reinforcement learning had no signal to learn from. It didn't know how to produce targets that will satisfy SLO, and that's why it's produced a bad policy. Because I felt the figure 6 from the paper alone wasn't enough to show a comprehensive comparison, I extended it to include the two baseline, which is K at SCPU and K at SCPU fast. And even under this extreme overload, Autothrottle still has lower overall latency and far lower CPU allocation compared to the two others, which directionally validates the paper's claim. So the next question is how the captain will react to the bad total targets produced by the tower. To answer that, I also reproduced figure 12, which shows how the captain tracks the tower's total targets. In the paper, the captain tracks the tower's total targets quite closely. The external ratio follows the target ratio with a reasonable fluctuation. Well, in my results, the bad policy, which produced by the bad training, produce a throttle targets graphs that are more erratic, with the actual throttle ratio barely tracks them at all. And to see the more detailed results, in this table, it shows the aggregate picture across all three workload types and all four workload types. And in the paper, Autothrottle achieves 14 to 26% lower CPU than the baselines, while in my reproduced results, the reduction is even bigger, around 27 to 49%, which I think it's quite consistent with the cluster being overloaded, and then which under server overload, reactive controller like key at a CPU over provision aggressively, while autothrottle's throttle-based approach keeps allocation more controlled, even without a good policy. Based on the paper, I also identified several gaps that can be extended. So Autothrottle currently only controls CPU concurrency using CPU throttle, and it leaves at least three gaps. Memory, which is fixed at pod creation with no runtime feedback. The second one is storage I/O, where there is no per container throttling, and the third one, which mentioned in the paper, is a replica count, where there is no horizontal scaling management. And I choose to dig deeper into the memory gap. My proposed direction is using a PSI-driven memory soft limits control via reinforcement learning. So PSI, or pressure stall information, is a Linux kernel metrics that measures how long tasks are stalled waiting for memory. So it's giving us an early warning signal before latency is actually impacted. And memory.high is a C-group V2 soft limits that throttles a container's memory location when exceeded and triggering background decline without killing the process, which potentially reduce overhead. And the hope is that by tightening memory.high proactively using PSI as a feedback signal, we can reduce DRAM usage while maintaining the same SLO. And my idea is to create new reinforcement learning on still using Fabula bit by adding PSI, specifically the average 10 as an additional context channel alongside the RPS. And the action space will be a discrete set of memory.high divided by memory.max. So memory.max is the hard limit that if exceeded triggers an out of memory kill, which range from 0.5 to 1 for the action space. And so this way, the controller always keeps some room below the hard ceiling. The cost function has three cases. So the first one if SLO is met and PSI is low, we reward tighter memory limits. So we push tighter memory limits. And if SLO is met but PSI is high, meaning there are pressure that is building, we apply mild penalty of 1 to 2 points to back off before pressure accumulates. And if SLO is violated, we apply a heavy penalty of 3 to 4 points. And for the exploration, we still use the epsilon greedy, and to make it reflect the memory risk, the racing memory.high will be weighted higher then lowering it. And lastly, I am motivated to contribute to research in learning-based resource control, either in surfing or microservice systems or other systems in general. I'm also willing to dedicate 30 plus hours per week on research collaboration as I prepare for PhD application in fall 2027. Thank you for your attention.